the key here when we're doing these two sample Z procedures, and it's just in general, you could, when you're talking about either a test or an interval, we could just in general call the procedure two sample Z procedure for the proportion from a population 1 minus proportion from a population 2, right? The only key real thing here to think about is what's happening with our formulas for the standard errors, right? So what essentially, what are we doing here? Well, let's see, we've got some population here, and here we have some other population, right? So like, let's say this is the population of something. Let's say this is the population of, say, seniors, right? And we could say this is the population of, say, freshmen. Let's do a big distinction, right? Right. And then we might say, like, let's define some parameter P as sort of the true proportion, like who, I don't know, have a book bag that weighs over I don't know 10 pounds. Like, here's my question. Do you think that that the proportion of seniors that have a book bag that weighs over 10 pounds is the same as the proportion of freshmen, right? So we could call this like PS, right? And we could call this like PF, right? Do you think that these two are equal? Evan, I'm with you. Absolutely not, right? And so what the kind of essence of what we're learning here in the two sample Z procedures for P1 minus P2 is thinking about the inferential techniques that we could compare the difference between these two things, right? If we were doing a significance test and we were thinking about these things, we might start with the null hypothesis HO, that PS is what compared to PF? What symbol would we use? Yes, equals. We might begin with the null hypothesis that PS is equal to PF, that the proportion of seniors that have a book bag over 10 pounds is equal to the proportion of freshmen. And then the alternative, which do you think would be the most logical alternative for us? PS and PF. What might we think, right? Yeah, I would say that this is in fact a less than situation, right? I'm with you guys. We would assume that seniors would be less than the freshmen. And so what the first thing we would have to do, though, is we'd have to convert this over to a different statement. And we did a bunch of stuff like this earlier. And one of the reasons we did a bunch of stuff like this earlier, because I wanted to prepare you for this logic here, right? Unless it's Vincent. Vincent, you have a heavy book bag. Anyway, I'm so proud of you, man. I always had a heavy book bag too myself. I actually, freshman book bag. I dig it, Kate, right? Actually, when I was in high school, I would never go to my locker except to take off. When I went to high school, I actually had to wear a jacket, like a shirt and a tie, and even like a blazer every day. But I would take my blazer and I would stick it in my locker, and I'd leave it in my locker until I got to school the next day. I'd take it out, put it on, wear it to class, end of the day, stick in my locker. But my books, I just kept in my backpack all the time. So I always had a freshman book bag too. But anyways, so the key idea here is that the null hypothesis will turn into a difference. If we just subtract, say, the proportion of freshmen from both sides, then we would just have PS minus PF is equal to 0. And over here, we would have like PS minus PF is now less than 0, right? And so these would be our hypotheses. Now, this is if I was doing a significance test, right? And this is essentially what I'd set up. If I contrasted that, all this would do is try to collect evidence to prove that the proportion of seniors that have a really, really heavy book bag is less than the proportion of freshmen. But that isn't like all that exciting and deep, right? Instead of trying to just prove that the proportion of seniors is less than PF, we might make a confidence interval, right? So if we made an interval instead of doing a significance test, then what we'd be trying to do is we're going to try to actually estimate what that difference is. What is the difference between, say, PS minus PF. Now, would you expect this difference to be positive or negative, the way I wrote it? What would you say? PS minus PF. Do you think the difference is going to be positive or negative? Well, I see Dominic chiming in with a dash, which is a negative sign, and Dominic is correct. I would assume this is negative because if I wrote PS minus PF, I would expect that this thing is going to be smaller than this one, and so this should be a negative difference. It doesn't really matter, but it's important that you pay attention to the sign because you would interpret it differently. If actually I made a confidence interval and I had an interval that was entirely negative, it's very different than an interval being entirely positive, because if you had an interval that's entirely negative, then that's just like saying that PS should be less than PF and stuff like that. So anyways, the core idea is there. But the fundamental thing here, so we'll either do a test or we'll do an interval. And when you watch the videos today, you'll learn to do the test and you'll also learn to do the interval. But the key mathematical difference that's going to happen in these things, aside from the fact that when one of them we calculate a p-value and the other one we don't, the fundamental difference is going to be in terms of how we calculate and use a standard error, right? And so and if you're doing a test, right, there's actually going to be a slightly different standard error formula for when we calculate our test statistic versus when we are calculating the standard error that will go into our margin of error, right? So for a test, the standard error of, say, p hat 1 minus p hat 2 is going to be the less intuitive of the two. The interval one is going to be the one that's more intuitive, right? So the standard error of p hat 1 minus p hat 2, in this context, 1 and 2 I could replace with like an S and an F. The key idea here is that for this one, you would just use whatever sample statistics you had. So let's say we collected, it's not good to make data up, but I'm going to make data up. Let's say we found, say amongst the seniors, let's say here, amongst our seniors, let's say we found that there was, I don't know, like 20 out of 100, that's probably even too high, that had these really heavy bags. But then amongst the freshmen, let's say it was something like, I don't know, maybe like 55 out of 100, and I don't, maybe that might be too low. I don't even know. I'm just making this junk up, But in this case, then these would be my two p hats. Like this would be p hat S and this would be p hat F, right? And so what I would do for the interval is if I'm trying to make an estimate, the standard error that I would use to make my margin of error is simply going to use these two p hats, right? I would do the exact p hat S, 1 minus p hat S, all divided by NS, the number of seniors I had, and I'll add to that, because you always add variances. I would add p hat F times 1 minus p hat F. I just drew on my wood. Divided by NF, the number of freshmen that I had, right? In this case, they both had 100 because I just made this data up. Now, what's different here? This formula is for a test is going to be almost the same, but there's going to be a fundamental difference. So if you watch the videos already, you'll see what it is. If you didn't, did anyone watch the videos yet? I'm just curious. I'm just asking. Anyone want to say yes or no? I mean, obviously, I didn't expect you to. I think I technically only posted. I actually recorded them last night. Because I was trying to get a little bit more done. So I had more time this morning to get some different things done. Did anyone look at them? Oh, David did. Yay. Nikira didn't. That's okay. No worries. Hey, Nikira. Evan only watched up to video 15. I think the videos go up to 17 now. But anyway, the key difference here is going to be something extra special, right? So we're still going to have a big old square root, and we're still going to have something that looks like this. Yeah, you're right, Evan. You did everything you're supposed to. If you watched up to 15, then you're good. Last night I posted some more, and then today I actually posted those videos that I uploaded to YouTube yesterday to Google Classroom. So you're up to date. If you've already watched up 15, you're ahead of most of my students. But here's the key idea. What changes here? And there's something special. I actually explained this in both the videos, but I want to explain it to you guys here as well too. That when you're doing a test, you're beginning with an assumption, right? The null hypothesis is that PS is equal to PF, right? In other words, that the proportion of seniors that have a heavy book bag is supposed to be equal to the proportion of freshmen, right? And so if that's the case, when we're calculating our standard error, let's capitalize, right? Let's capitalize on this assumption, right? If this is really our assumption, right? Let's use it for all it's worth, right? What do I mean by that? Well, do you agree that when I'm doing this significance test, I actually don't care what proportion of seniors have a bag that's over 10 pounds, and I don't actually care what proportion of freshmen do. The only thing I'm trying to say is that it is equal, right? So they could both be 80%, or they could both be 40%, or they could both be 10%. And I actually wouldn't care. And it wouldn't make any difference to me whatsoever in terms of whether I reject or fail to reject the null hypothesis. All I'm trying to do is to try to prove that, in fact, one is less than the other, but I'm beginning with the assumption that they are both equal. I don't actually care about the values. And so when I say this is equal to this, I'm going to capitalize on this assumption to try to come up with an estimate, to try to arrive at an estimate. I want to arrive at a quick estimate. Let's arrive at a quick estimate for P, right? Remember, P in general almost ignored whether it was seniors or freshmen. P in general was just the true proportion of, say, students at Central that have a book bag that weighs over 10 pounds, right? And so if I assume that P is going to be the same in seniors as it is in freshmen, what I'll do is I'll create a combined sample. All right. So, and this is something that, again, I'm explaining in more detail than I even do in the videos, but I'm really trying to make sure it's the only weird thing that goes on. I'm going to create a combined sample to estimate P. So, in other words, right, in a little made up data that I had here, so I had 20 out of 100 seniors that have a heavy bag, and I had 55 out of 100 freshmen that had a heavy bag. So if I was to try to put that together, right, then my estimate for P could be something like, oh, well, altogether I had 100 plus 100 people, right? And then altogether there's 20 of them were seniors and 55 of them were freshmen. And so altogether, if I was to combine stuff up, I would estimate that actually what P was something like 75 out of 100. That only works because, again, I assume that it should have been the same in seniors and freshmen. So I could combine all the results together to get like this just one big sample. And so 75 divided by 200 is 37.5%, right? So this would be an estimate of 0.375. Now, in terms of notation, technically, this is not what P is. It's still an estimate, just like P hat is an estimate. And so we will use the little P hat symbol, but this isn't like a plain old P hat, like the P hat from seniors or the P hat from F. And in the calculator, it actually just represents this as P hat, but we'll frequently use an AP stat, an extra little bit of notation like a little C there that communicates that this came from a combined sample, that we combined our samples together. Another name for this is called pooling, like you pool everything together. And so that's the only real key difference here. When we come up with the formula for the standard error for a test statistic, instead of using a separate P hat from S and a separate P hat from F, I'm going to use this combined pool. So I'll do something like P hat C times 1 minus P hat C over NS plus the same thing. Excuse me. P hat. Gosh, I'm sorry that I'm like coughing into my microphone. Was that loud and annoying to you guys? Over NF. Let's see here. I'm going to get a little color to divide stuff. Oh, thanks, Kira. Anyway, that's an ugly color. What color is that? Oh, that's weird. But anyway, So if we notice here, and like let's really zoom in now, right? The key difference here is that when I'm doing the test, I'm going to use this combined estimate for p hat when I'm making my test statistic, and for the interval, I'll actually use the two separate ones. Again, the real reason why in a test, I make this assumption that PS and PF should be exactly the same. But when I'm doing an interval, I'm trying to estimate what this is. And my assumption is not that they're equal. If my assumption was that they're equal, then my estimate should just be that they're zero and move on with my day. But I'm actually going to try to come up with what I expect this to be. And so since there's no assumption of equality, I will keep things separate. But here, since I do have an assumption of equality, I will pool in this way. Right. And so anyway, that's the real, only mathematically, that's the only subtle difference. Everything else follows our expectations, in my opinion. There's nothing fancy. When we do the full procedure, you'll check the same kind of conditions that we always do. There'll be large counts because we're dealing with proportions. You can do everything just in the calculator, right? So like if I'm being lazy, in fact, here, let me do a test and an interval just in the calculator for these data right now. So if I say I did a test first, I could go to test and I could go to 2 prop Z test, and I could put in these facts. And so what I had 20 out of 100 seniors, and then I had what did I say? 55 out of 100 freshmen. And I was trying to do a left tail test that the first one is less than the second. And I can hit calculate, quit domain. What did I do? Someone tell me what I did. 2 prop Z test. Let's look again. Oh, I wrote 200. Ha! Did anyone notice that I wrote 200 for X1? That's why I got a domain error, right? So X1 is 220, N1 is 100, 55, 100, left tail test, hit enter, and Shazam. This says that that's a crazy test statistic, and I got a tiny p-value, and so I would reject the null hypothesis. And notice here, this little p-hat right there, p-hat 0.375, that is the p-hat that was obtained by our pooling. That was our estimate for using a combined sample for what we should have for our p-hat. So that's cool. If I was to do an interval, then I could just go over here and I could go to a 2 prop Z interval here in B, and I already has all the facts. If I did a 95% level of confidence, I could hit calculate, and there's my estimate. So this is a huge interval, actually, right? Notice though, it's entirely negative. I'd estimate that the difference between the seniors and the freshmen, the difference in the proportions of senior and freshman that have really heavy book bags is somewhere from negative 47.5% to 22.5%, a really wide interval. Why is that interval so wide? Mostly because why? Let me ask you this. Why do you think that interval is so wide? And what could I have done to make the interval much less wide? I'm going to throw that question out there. What could I have done? What in this situation would lead my interval to be much tinier and a more useful estimate for the difference between PS and PF? Let's see here. I'm killing time. Kate chiming in very quickly. Kate says, increase the sample size, right? What did I say, Evan? Negative 0.2249. It does say that. So it's like around negative 22.5%. Did I say something different? I don't even know. I probably did. I apologize. But Kate, you're right. This sample size was small, only a sample size 100 in both cases. And so that means that there's still going to be a lot of variability in the results. And so even though with that sample size, it was possible to detect with significance that I should reject the null hypothesis. I mean, I didn't even set up a level of significance here, but the p-value is so small, it doesn't even matter. I would still reject the null hypothesis. So the sample size is big enough to disprove that it's equal, but to get a really good estimate of exactly what the difference is, you would definitely want to take a bigger sample size. I mean, I could have also shrunk my the width of my confidence interval. I could have shrunk the margin of error, not by increasing the sample size. I could have done it simply by taking my level of confidence and either going up or down. Which is it? Which would shrink the width of my confidence interval? Increasing my level of confidence or decreasing my level of confidence? Anyways, you do want it to go down. Now, just having less confidence is not as useful or interesting as a way of shrinking your interval. A better way to get a narrower interval here would be to just get a bigger sample size. Considering 100 wasn't that enormous of a sample size anyways, it would be worth trying to get some more.